Hey guys, the objective of this video is to find the ultimate moment, and this is with the hogging moment, ignoring the bottom steel. We're going to be using section 8.1.3 of AS 3600 to allow us to do this. So I've just drawn the progression we're going to be doing. Now we're looking at hogging, so our section looks like this. For hogging, our ruler is going to bend up like that, which means that the top is in tension, the bottom's in compression. I've drawn in also 47 and 549, we found that in the previous video, just the distance to the center of the steel layers from the bottom. Okay? Now, we're going to first go to the strain diagram. So we go over to section 8.1.3, and I'm going to zoom in. So in section 8.1.3, we have the rectangular stress block. Okay, so it says the rectangular stress block deemed to satisfy for the concrete, assuming that the maximum strain in the extreme compressive fiber is taken as 0.003. So let's just deal with that first. The strain in the extreme compressive fiber. So as we said, the compression is down here, so the extreme compressive fiber is going to be down there. Its strain, the code told us, is 0.003. Okay, so that's what we've taken from the code. Now for the stress diagram, we're also taking from the code. It says that a uniform compressive strength, let me zoom in, alpha 2 FC dash, so the stress alpha 2 FC dash, which I've done there, acts on an area bounded by the edges of the cross section, so that's the width, and a line parallel to the nucleus axis under the loading concentrated and located at a distance gamma KUD, which I've just summarized to be gamma DN, because in the previous video I said DN is the same as KUD, which means gamma DN is the same as gamma KUD from the extreme compressive fiber, where alpha 2 equals that and gamma equals that. Okay, so we're going to be seeing that now. So once again, from the code we extract the maximum strain in the compressive fiber as well as the rectangular stress block. So we're first going to be working out the concrete. Now we're going to want to find the compression in the concrete, and again this example is ignoring bottom steel. Okay, so we're not including anything in the bottom steel, we're completely ignoring that. In the next video we're going to be looking at including bottom steel. So the only thing we have at the bottom is in the concrete in compression. So we're going to find the concrete in compression by working out the stress times the area. Now, the stress we said in the code was given to us by alpha 2 FC dash, and the area is going to be gamma DN, which is the height over here, times by B, which is the 200 there, okay? That's from 8.1.3. We can find alpha 2 and from the code in gamma. So alpha 2, if I zoom in for you, alpha 2 is 1.0 minus 0.003 FC dash within these limits, okay? So alpha 2 is 1.0 minus 0.003 FC dash, where alpha 2 has to fall between there. Now our FC dash is 40 MPa, so outside of 40 gives us 0.888, okay? Which is outside that range, so we need to take the value 0.85, okay? Because alpha 2 has to be between there. Gamma, also from the same section. So gamma is 1.05 minus 0.007 FC dash, where gamma falls between that range. So I've just written it out there bigger. So, subbing in for 40 MPa, 1.05 minus 0.007, 40 MPa gives us 0.77, okay? So 0.77, that falls in that range, so that's good. Alright, so we've now worked out alpha 2 and gamma. We can then work out the compression in our concrete. So again, the compression in our concrete is given by that formula there. It's just the stress times the area. Working this out, we just found alpha 2 to be 0.85. FC dash is 40 MPa, gamma we just found to be 0.77. DN, we don't know what that is, that's what we're trying to solve. And B is the width. Now because we're looking in hogging and the compression's down here, the width is this width over here, so our concrete in compression is only going to act over that width, because everything above the neutral axis is cracked, okay? So that width is 200. For the sagging case, it would be the opposite. It would be that width up there, so the width would be 760, okay? We're doing hogging, so we're looking down at 200. So the width is 200. Solving this, 0.85 by 40 by 0.77 by 200, by 200, gives us 5236 DN, alright? So that's for the concrete. Now for the steel. Because we're looking at the ultimate moment, we're going to say the steel in tension is at yield. This isn't always the case. In the videos where we find a column in different situations, the moment the steel is not always going to be in tension, then we have to assume a steel. But for the ultimate moment, we're going to say that the steel in tension is at yield, all right? Which means that the tension in the steel is just going to be the yield stress, FSY, the steel in yield, times by its area. Now, we said we're using 500 bars. The bars we're using in our problem are all 528s, all 500. So it's 500 MPa times by the area of steel. Now, in the top, we had N28 bars, so the radius is 14, and we have 2 of them. So it's 2 by pi by 14 squared. So 500 by 2 by pi by 14 squared gives us 615,752 newtons. All right. Now, once again, this is steel in the top. We're trying to find the steel in the top because we're hogging, and that's where the tension steel is. It's in the top. And again, we're ignoring the bottom steel, so we don't need to include that. In the next video, we will be including it, but for this video, we're not doing it. Okay, so continuing on. For the bending case, for ultimate moments, so this is what we call pure bending. There's only bending in our beam. We can say that the sum of the compression equals the sum of the tension. So, the compression in the concrete, 5236 dN, equals the tension in the steel, which is 615,752. So solving this, 615,752 divided by 5236 gives us 117.6 millimeters. Okay, so we now know that the depth to our neutral axis from the extreme compressive fiber is 117.6. We can also find gamma dN, the height of our rectangular stress block. So all we need to do is just multiply dN by gamma. We found gamma to be 0.77. So 0.77 by 117.6 gives us 90.6 millimeters. And the last thing we can do is just find the compression in our concrete. Now we know it's going to be the same as the tension because we set it here, but we can just show that. So the compression in the concrete will be 5236 times dN. So 5236 times dN, which dN is now 117.6. So solving this, we'd get 61572, which is the compression in the concrete, which is the same as the tension in the steel, which it has to be. And we can show that the compression in the concrete equals the tension in the steel. The last thing we're going to do now is actually just find the moment. So just to show you how we're going to do this, we just need to find lever arms of the concrete in compression and the tension in steel. Now, this compression in the concrete acts at the center of the rectangular stress block. So this height is gamma dN, which means that the height from the bottom, that height there, will be gamma dN on 2. Okay? So the height of the compression in the concrete acts right in the center of the rectangular stress block. So it's going to be gamma dN on 2, and the tension in steel acts in the center of the layer, which is at 549. So if I just redraw that a little bit bigger to show you. So we have the tension in the steel acting at the center of the steel layer. So now you can see why we found it, which we saw in the previous video was 549. So that tension in steel, 615,752 newtons, is acting at 549 from the bottom. And the compression in the concrete is acting at gamma dN on 2. Gamma dN we said was 90.6. So it's 90.6 on 2. Gives us 45.3. Okay, so it's at a height of 45.3 millimeters. So that's where they are. And to take the moment, to make it simple, we can, because it's pure bending, you can take moments about whatever point you want. To make it simple for us, we're going to take moments about the compression, okay? Which means that this has no lever arm, which is all we need to do is find the moment from the tension in the steel. So we're going to say that the sum of the moment, anti-clockwise being positive, is equal to the lever arm times, the force times lever arm. Okay, so the force is 615,752 times by the lever arm, which will be this distance in here, which will be 549 minus 45.3. Okay, so working this out, so 615,752 times by 549 minus 45.3 divided by 10 to the 6 to give us kilonewton meters. Gives us 310.2 kilonewton meters. Okay, so that's how you would find the moment. Once again, an important thing for pure bending is that you can take the moment about any point you want. I could have done it about there if I really wanted to, but to make it simple, you just take it about one of the forces. So that doesn't have a lever arm. So all you need to do is just find the moment due to the one force. Anyway, guys, hope that helps, and we'll see you in the next video where we do the same problem, but we include the bottom steel.